Problems for chapter 23, the Milky Way galaxy. So we're going to do problems 1 through 5 and 7. All right, so those are the only problems that we're going to do. So let's look at problem 1. Let's see. Sorry, those aren't the problems. This is the review. Here are the problems. Sorry about that. All right, so it says calculate the angular diameter of a pre-stellar nebula of radius 100 AUs lying 100 parsecs from Earth. Compare this with the roughly 6 degree diameter of the Andromeda galaxy. All right, so to do that, we're going to switch to right here. All right, and with that, this is of course the problem. The problems that we're going to do from chapter 23, 1 through 5. As it says right here, and problem 7. All right, so the first one I just read to you, and so there's a couple of things that we need to think about here. So it turns out, like if you think about like just a circle, it turns out there's a relationship between the length of something, and this would properly be called the arc length. Okay, so that's what the capital D is. D would be the distance to that object, or to whatever is making up that arc length, and then theta is the angular size, or the and the angular size has to be in radian. So the basic idea here is D, capital D, is the size of the object, or its diameter. Little d is the distance, and then theta is the angle in units of radian. And just to remind you, radian, with radian measurement, pi radian is equal to 180 degrees, or you could say 2 pi radian is 360, but you get the same thing. Note also that big capital D and little d, so capital D, remember, is the size of the object, little d is the distance, they have to be in the same units. All right, so the relationship is well, I didn't really write that, so here let me write the relationship is that that big D, capital D, is equal to the distance to the object times the angle that it makes up. All right, so they give us this information. They say that this nebula is 100 astronomical units, and it's 100 parsecs away. So what we have, so that's the relationship. But of course, big D and little d have to be in the same unit. So what we'll do is we'll convert little d from parsecs to astronomical units. All right, and so the way that we do that is we have to know. So this is still number 1. Little d, which is 100 parsecs. It turns out that in 1 parsec, so 1 PC, that's supposed to be a 1, is equal to, let's see, where do I have it? Oh, here it is. Exactly, it turns out to be 206,000, and we've seen this before in lab, you might remember, 206,264.8 astronomical units. All right. So that's what 1 parsec is. So, if you multiply by 100, that turns out to be really, really simple. It turns out to be, you just move the decimal place 2 places to the right. So 206, 264, and then 8. Well, let's see. So it's it would be 80.6. It turns out. Okay, so I had rounded this part right here. So it's actually exactly 0.806. So anyhow, so if you multiply by 100, that's the actual number, and so 100 parsecs is that number, and so now we can actually work out what theta is. All right, so now remember, theta is going to be in radian. That's important to remember that. So it's going to be 100 astronomical units, right? And see, now the astronomical units will cancel, divided by 206, 264, 80.6 AU. Right, so that's what 100 parsecs is, and so the AUs cancel, and so this will give us our answer in radian. This is a really small angle, by the way. It turns out to be 4 point, I'm going to round here somewhere, 4.848 times 10 to the minus 6th, 10 to the minus 6th radian. All right, and then, of course, we're going to use this conversion to get it into degrees. Here, let me scoot this down a little bit. So the conversion, of course, is that pi radian is equal to 180 degrees. So degrees. So I'm just going to use the little degree symbol, and so this is what theta is equal to, and we're going to make theta even. We're going to figure it out in arc seconds in just a moment. All right, so it's 4 point, you could say 85, 848. It doesn't really matter. I already have that in my calculator, so I'm going to 848 times 10 to the minus 6th, 10 to the minus 6th, and of course that's radian. That's rad. All right, and so we know that there are pi radian in 180 degrees. All right, 180 degree. I'll write degrees just to make sure that that's clear. And so the radians cancel, and so you just multiply that this number 4.848 times 10 to the minus 6 times 180 over pi. And so you get, let's see, what do you get? So you get 2.78 times 10 to the minus 4th degrees. That's 10 to the minus 4th degrees. All right, and then what we're going to do is we're going to change that into arc seconds, right? Because arc seconds are, fractions of an arc, 1/60th of an arc minute, and then of course one arc minute is 1/60th of a degree. So we'll further. So you just take this number here. I got a little bit of room right here. So you just take this number. So it's 2.78 times 10 to the minus 4th, 10 to the minus 4th, and of course it's degrees, so I'll use the degree symbol. But of course we know that in 1 degree there are 60 arc minutes. Remember, arc minutes, you can use the double, the single hash mark, arc minutes, to represent that. And so we know that in so this single hash mark also means arc minutes. That's also equal to 60 arc seconds. Right? So you basically, the degrees cancel, the arc minutes cancel, and so that'll leave you multiply this number by 60 squared, and you get, let's see, what did I get? Just a second, let me, where's my mouse? All right, let me pause it for a second. So, we take this number in degrees, we multiply it by 60, that changes it to arc minutes, then we multiply by 60 again, that changes it to arc seconds. So that turns out to be the angular size of this object is 1 arc minute, approximately 1 arc minute. All right, and then they ask us to compare it to Andromeda, which, this is ridiculously smaller than Andromeda. Andromeda has an angular diameter in the night sky of about 6 degrees, right? 6 degrees. So that would be like, just to give you a sense of that. Yeah, there's no way it's that big. Hold on, let me look it up. That's what they say in our textbook. They might have mistyped it. Hold on, let me look it up. All right, as I thought, I just looked this up. So Andromeda is about 3 degrees in size. The angular size of Andromeda, when you look at it, the Andromeda galaxy is about 3 degrees. So if, remember the full moon is about half a degree across. So they just got it mixed up a little bit when they did this. See, it says compare it with roughly 6 degree diameter of Andromeda. It's actually really just it's actually 3 degrees. Okay, so that's just a mistake that they made. All right, so let's go back to this problem. So again, this is I should have caught that that's not right. So it's not 3 degrees. It's not 6 degrees. It's approximately 3 degrees. Not that that matters anymore. Doesn't matter very much at all, because of course 3 degrees is much bigger than 1 arc second. Okay, so that's the point. All right, let's move on to the second problem. So here, actually, let's just go switch here. And so here's our second problem. How close would the nebula in the previous question have to be in order to have the same angular diameter as Andromeda? All right, so we're going to have to rework this problem for 3 degrees. I think I worked it without thinking about it. I had worked it for 6 degrees. Anyhow, and then calculate the apparent magnitude of the central star if it had a luminosity 10 times that of our sun. All right, so we got to work on that. All right, so as I just looked up, the angular size of the angular diameter or angular size of the Andromeda galaxy is really 3, not 6, as it says in the problem. So we'll work it using 3. All right. So anyhow, what that means, of course, is that theta. Here, let me do this over here. So theta, we got to change that into radian, is equal to 3 degrees, and then of course 3 degrees, and we know that pi radian is equal to 180 degrees, 180 degrees, and then of course the degrees cancel, and so it's just 3 times pi divided by 180. So theta is equal to, let's see, what is it equal? So theta is equal to, what do I have? 0.052 radian. 52 radian. All right. And from that, we can figure out, what the question asks is, what does little d, or sorry, what does capital D have to be? What does little d, the distance, have to be if capital D is 100 AU? All right, so this is the angle in radian, and if you remember the original distance, or the original diameter of this was 100 AU, so that puts this thing a distance of 1,909.9 astronomical units. Then we convert it into parsecs because we need it to be in parsecs, and it turns out to be 0.009 parsec. All right, I'm going to finish this one up quickly. So we figured out the distance would be 0.009, and then they say figure out the apparent magnitude. All right, so we have to figure out the absolute magnitude. There's the absolute magnitude of the sun times minus 2.5 times the log of 10, because it turned out to be 10 times the log. Anyhow, when you do all this, you get an apparent magnitude of negative 12.9. That's like the brightness of the full moon. So this thing would be extremely bright because it's this. It would have to be this close to us.